Hello, I'm Lance. I'll be talking about a FAEST signature scheme, or FAEST. We currently are disagreeing among authors which pronunciation is better. I will use FAEST. All right, so FAEST comes from a line of food-based signature schemes, or signature dishes, I guess. So there's picnic that was submitted to the previous competition. FAEST is more directly based on barbecue and banquet. Barbecue switched to using AES as the one-way function. So we're bringing to you a FAEST. All right. So FAEST is a signature scheme based on a zero-knowledge proof called publicly verifiable zero-knowledge and post-quantum signatures from VOLE in the head. Now, putting voles in people's heads may sound kind of gruesome, but I can assure you no voles were harmed in the making of this presentation. All right. So where does this fit into zero-knowledge proofs? Well, so generally speaking, there's like some zero-knowledge proofs are succinct. They are sublinear in size in the witness, such as Lagaro or Stark's, but they typically require a longer time to prove and also have some higher startup costs associated with them, like in terms of proving when you have something very short you want to prove. It can be expensive just to get started. Linear proof sizes are on the other end of the trade-off that can be very fast, such as MPC in the head schemes. And what we're interested in is VOLE-based zero-knowledge proofs, which can be even smaller and faster than MPC in the head. However, they have a problem, which is that they are a designated verifier. You can't build a signature scheme out of a designated verifier proof. So VOLE in the head is a general tool for making these VOLE-based zero-knowledge proofs publicly verifiable. So for FAEST, we want to have security based on just AES and SHA, and we want to have good performance. And the cost will be that it will be a linear size proof, which is going to be like 11 to 16 bits of communication for every bit of the witness we're proving for the 128-bit setting. Let's first look at how VOLE-based zero-knowledge proofs work, the traditional designated verifier VOLE-based zero-knowledge proofs. So VOLE stands for vector oblivious linear evaluation. So what that means is that, okay, let's say the prover has some values u and v. It commits to u as its witness. It commits to u by choosing some random linear function, so ux plus v. The verifier has some secret value delta that this linear function is evaluated at to get some value q. And it's called vector because this will be done over and over again on a whole vector of u's and a whole vector of v's, all using the same delta. So it's scalar times vector multiplication. So this can be instantiated efficiently from several different things, most commonly either oblivious transfer or some combination of that with LPN. This can then work as a linear commitment scheme, a linear homomorphic commitment scheme. So to open a commitment, the prover can just send u and v to open its commitment to u. And then the verifier just checks that the equation, the correlation holds. And this is binding because if the verifier chooses the wrong u, they'll end up with a different linear function, p prime. Two lines can only intersect at most one point, so there can be at most one delta value for which these two polynomials agree, or these two linear functions agree in this case. And so there's probably at most one over the field size that the prover manages to guess a polynomial that intersects at the right point and so lies about the commitment. Additionally, these commitments are linearly homomorphic because this is just a linear correlation. If you want to add them together, well, the prover can add their u's and v's, the verifier can add the q's, and the same equation will hold. All right. So you can use linear homomorphic commitments to build a commit and prove style zero-knowledge proof. So how does that look? Well, to start with, we can have the prover commit to their witness U, and then evaluate it some circuit gate by gate. So the linear gates are really easy because they're linear homomorphic. We can just use the homomorphism. But multiplication, how do we do multiplication? Well, recently there's a very efficient multiplication check protocol published called Quicksilver. And this works by multiplying these lines into a quadratic function. So now we have these, these two lines representing these A and B inputs now get multiplied to the quadratic, the yellow parabola. And now I see the PAB is this polynomial. Notice that the highest degree term of this polynomial is going to be the product of the two committed values. Now, if you want to check that this value is C, we can take the difference to another polynomial that has C in that highest order term, and then the highest degree terms will cancel out, and we get a degree 1 polynomial. So what that means is that the prover can open this degree 1 polynomial. The verifier makes sure that it's degree 1. And then if this polynomial agrees with the verifier's half the correlation, then the check passes. So the verifier's half the correlation will be Q1 times Q2 plus Q3 times delta in this case, or minus Q3 times delta. Now, of course, this leaks to open the polynomial, but we can mask with a random commitment first to hide it. So what's this look like in terms of communication cost? For each gate, the prover must commit to the output C, and then they must open this mask commitment. However, the opening, it can be amortized, as can the masking, because if you have a set of polynomials to check, you don't need to check them all individually. You can take a random linear combination of them. If at least one of them has an error, then a random linear combination will have an error with high probability. So this means for a circuit, if m inputs and n multiplications, the prover only needs to send m plus n field elements, assuming the most efficient kind of LPN-based VOLE. And there's been various improvements of different kinds to this area, like higher degrees or other things. All right. So how do we make this publicly verifiable? So start off looking at what MPC in the head. So MPC in the head, there's the prover divides their witness into n secret shares, does some protocol, MPC protocol imagines it. The verifier samples a challenge, which the selection of which party they will not see. Then the prover sends the n-1 parties that they are allowed to see, all their views. And then the verifier will check all this. So it turns out this is structured very similarly to a protocol for generating VOLE based on oblivious transfer. So this is the soft-spoken OT extension, but it's also a VOLE. Yeah. So again, there's this value U that's the VOLE value, and we have additive secret shares of it. Now instead of this commitment, there's an n-1 out of n OT. So the verifier has some secret index delta that chooses which of these they will not receive and which they will receive. So they will receive UI for all I except for delta. And then there's a calculation that the two parties can perform to get the VOLE correlation. The prover can calculate negative I times UI, summed over all I. The verifier can do the same thing, offset by delta, if I offset by delta. Then the idea is that when I is equal to delta, that when I equals delta, the coefficient on the right there becomes 0. So they don't need to use U delta. So it is something you can compute. And then you can just check algebraically that the Q will equal U delta plus V because of this, just by expanding the sum. All right. So that's based on oblivious transfer, so it can't be, it's still designated verifier. To make this publicly verifiable, We use a GGM tree similar to the hypercube scheme to do an all-but-one vector commitment. So commit to n different random strings. The verifier samples the challenge. We open n-1 of them, and then convert to this VOLE correlation as before. Now the thing is that the VOLE was only secure as long as delta remains secret. If delta is revealed, that lets the verifier, that would let the prover cheat when opening the commitments. So it seems like a problem, right? Well, the trick is that to run the VOLE zero-knowledge proof before the VOLE completes, after do the commitments, but before delta is sampled. That way, so after the proof is over, it doesn't matter if the prover gets delta. They've already committed to everything. So this is how we can make it. Running the proof, it seems like it's too early though, because the verifier doesn't know Q. But then luckily everything the verifier is doing in the proof is just sending random bits, which they can do anyway, or doing checks at the end, which can be delayed until after Q is opened. So some more details. There's this gives from this n-1 of n vector commitment, we get a field of VOLE in a field of size n, which means it only has soundness error 1 over n, so it's inverse polynomial. So we'd like to get this down to exponential error. So we want to get an exponential size field. So we can repeat it tau times to get it into fn to the tau. If we repeat it with the same witness, every time we repeat it, we need to send communication proportional to the witness size. And finally, we need a consistency check to make sure the prover actually sent the same thing every time. So for the consistency check, we use a consistency check from OTA extension, which I'll skip past now. All right. Okay. We use this to prove one-way function. This one-way function will be AES. So let me back up a sec. The way we can construct a one-way function from some certain encryption scheme, we want to prove the knowledge of some secret key that maps some public input to the public key. Prove knowledge of this secret key. So we want to do something standard, but it's also we want it to be something efficient to prove in zero knowledge. It turns out AES has some nice structure to it that helps to prove it in zero knowledge. In particular, most of the operations are linear. The one nonlinear operation is the S box, which is inversion in F2 to the 8. Inversion is something that can be checked efficiently because it's just a single multiplication to check. Like if y is x inverse, then x times y equals 1. So more detail, what happens is the prover commits to the full key, the internal state of every round of the block cipher, and also the internal state of the key schedule. This, for AES 128, that amounts to 1,600 bits of commitments, which needs to be multiplied by a tau for the communication cost. And then there's 200 constraints, one for every S box. Luckily, with this Quicksilver check, the constraints are more or less free because we can just take random linear combination as before. However, there's one problem with this. What if we try to take the inverse of 0? In the AES box, the inverse of 0 is just set equal to 0 by just arbitrarily. But that isn't compatible with the algebraic structure. So it won't check properly. So what we do is we just sample a key for which this never happens. There's for every S box, there's there's only a 1 in 256 probability of a problem. So it turns out to be a fairly good probability that a random key has this property. So we only lose a couple bits of security at most. Okay, so to summarize, the prover commits to their secret key and the state of the block cipher. After this commitment, in their head they have this correlation. They don't know delta yet, so they don't know Q, but they know that they've committed to this U and V, so that the correlation will hold. Then the verifier samples the challenge, the first challenge, which is used to prove the VOLE consistency check, to make sure that all the different witnesses were the same. Then The verifier will sample a second challenge, which is then used to do a random linear combination of the polynomials to check the multiplication constraints. Then finally, they sample a third challenge, which is this opening point delta, and the prover opens everything. And then the verifier can check all the openings. So notice all these challenges are just public random values now, so we can just use fiat Shamir transform to turn this into a publicly verifiable proof, non-interactive proof. All right, so we implemented this, and here are some benchmarks from my laptop. You can see the signature sizes are smaller than Sphinx on most of the code base candidates, and we can get faster signing, but it would be a slower verification compared to Sphinx. We also have a even Mansour variant, which means that, basically making the key of the block cipher public and having the input be secret. And because of the key is fixed, that makes it 10 to 15% smaller. But on the other hand, it's like a more less usual assumption to make. Right, we also have some work in progress for improving this. We want to make some improvements to the proof and protocol based on better domain separation to make sure the adversary can't attack multiple things at once in parallel. We can use that to make some tighter proofs. We want to tweak the parameters a bit. We think we can make the signatures a bit smaller and have faster verification. And we've also been looking into using other one-way functions. For example, for the pure multivariate quadratic scheme, we've estimate the size to be about 3 kilobytes. And also looking at the brain cipher as another alternative. So to conclude, VOLE-based zero-knowledge proofs are very lightweight and fast and have linear size. And VOLE in the head, they become not quite as lightweight, but they can be publicly verifiable, so they can be used to make a signature. And with using that to make the FAEST signature scheme, you get a scheme that has conservative security and reasonable performance. Thank you.